Alright, in this video we're going to look at finding the sum of a finite geometric series. Finite means it doesn't go on forever. So we're just going to dive right into it here. How we come up with this formula is a little bit similar to how we came up with the arithmetic series one. But the sum of the first n terms of a geometric sequence is given by our sum, or s sub n, where n is the first n terms, is going to be our first term, whatever that value is, times 1 minus our common ratio to the n power, all over 1 minus our common ratio. So we're going to be working with that in this video. Infinite series actually have an easier formula than this. It's very similar to this, and there's a piece missing. But for this one, we're going to look at finite geometric series, ones that actually do end. So example 5, we have 0.5 plus 2.5 plus 12.5 plus yada 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 plus 39,062.5. So because it ends at this value, that's why we call it a finite series. Well, looking from one term to the next, it's not gonna, we're not adding 2 every time, but if we check the ratio, 2.5 divided by 0.5, 12.5 divided by 2.5, etc., our common ratio is 5. So we multiply by 5 to get from one term to the next, which means our series here is geometric. So we can always check at the start if it's arithmetic or geometric. So our y-intercept would be 0.5 divided by 5, or 0.1. So our rule is 0.1 times 5 to the n power. And to get our lower limit of summation, we can set our rule, or solving for n rather, because we know our lower limit is going to be 1. But to get our upper limit, if we solve for n, we can divide both sides by 0.1. We get 390,625. And then take log base 5 of both sides, and we get 8 for n. So if we plug this into our calculator, we end up with 48,828. In terms of our rule, we had n equals 8. So our first term was 0.5 times 1 minus our common ratio of 5 to the 8th power all over 1 minus 5. And if we take 0.5 times 1 minus 5 to the 8th power and divide that result by 1 minus 5, we'll get 48,828. Part B, we're going to write it in sigma notation and find its sum. So we have 2, then negative 8, then 32, then negative 128, all the way up to 33,554,432. Well, first let's check if it's arithmetic. From 2 to negative 8, we'd have to subtract 10, but negative 8 minus 10 is not 32, so it's not an arithmetic series. If we check the ratios, negative 8 divided by 2 is negative 4, 32 divided by negative 8 is negative 4, negative 128 divided by 32 is negative 4, so we do have a geometric series with a common ratio of negative 4. Which means to get our y-intercept, just take 2 divided by negative 4, we'll get negative 1/2. And our rule will become negative 1/2 times negative 4 to the n power. To get how many terms there are, our upper limit of summation, we set this rule, negative 1/2 times negative 4 to the n power, set it equal to your last term. So when we do that, we get, if we divide both sides by negative 1/2 or multiply both sides by negative 2, we get negative 4 to the n power equals negative 67,100, or no, excuse me, negative 67,108,864. Now, you can't take log base negative 4 of both sides. Instead, what you're going to want to do is ignore the negatives altogether. So it's going to give you the same answer if you just did 4 to the n power equals 67,108,864. So ignore this negative for our in front of the 4, and also the negative in front of the 67 million number. And if you take log base 4 of that 67 million plus number, you'll get n equals 13. So from 1 to 13 of our sequence rule, we get about 26,843,546. In terms of our rule, for traditional rule, our first term is 2, our common ratio is negative 4, and we said that there were 13 terms. So we would do 2 times 1 minus the expression -4 to the 13th power. And we would take that result and divide it by 1 minus -4. And we would end up with 26,843,546. I did again want to show you, start this video with the rule, the traditional rule, because infinite series, which is our next video, very similar to that, and we won't be able to put those into our calculator. So, all right, that about does it for this video. Thanks for watching. I'll see you next.